Oops. There we go. Good morning. All right, can you hear me? Can you see my screen? Hello? Can anybody hear me? Can anybody hear me?
Yes.
Okay. All right, so you can hear me now? Is that right?
Yes.
Thank you. That's great. Okay, good. Okay, it's 9:30. We'll get started. So we're looking at Module 12 today, bonding and structure. We'll first of all focus on electron configurations. And I think most of you are at least a little bit aware of the shapes of some of the orbitals and what the orbitals mean. But the orbitals that we talk about are basically volumes of space where we could expect to find electrons. So we have an s orbital, which is kind of spherical around a central point. And I use these x, y, and z axes to define a three-dimensional space. The p orbitals look like, well, I suppose they look like little barbells, I suppose. And those are along each axis here, the x, y, and z axis. There are 2 electrons in each orbital, and whenever we place electrons in an orbital, we always do so with opposite spins. So one will be up and one will be down when they're placed in the same orbital. All right, so let's talk about how we write out these electron configurations. And we do so in this kind of format, 1s2, 2s2, etc. Now the 2s, of course, are usually, I mean, these numbers here are usually superscripted. When you're writing out these numbers, you won't be able to superscript them. So I just go ahead and say 1s2 and leave the 2 as regular script when you're writing the answers. So what we need to do is define where we're going to find these different orbitals and which elements are going to, which electrons are going to be responsible for each kind of orbital. So we've got the periodic table here, and it's split into what are called blocks. So we have the S block, the P block, the D block, and the F block. So the S block are the first 2 rows or columns, I should say, on the periodic table on the left side. The P block is going to be the last six columns on the right side. The D block are the elements in the middle, and there's 10 columns in there, and the F block, there's 14. So already you can see a progression, at least as far as the number of columns are concerned in each block. 2, 6, 10, 14. So it's going up by 4 each time. So let's look at how we go ahead and number these. The other thing that's important, I think, because this does help with the writing out of electron configurations. Make sure I've got this the right way around. There we go. And that is that the S starts at 1s. Oops. And the P starts at 2p. The D starts at 3d. And the F starts at 4f. And I think if you remember that, then it makes writing out these electron configurations a whole lot easier. So here's the question. The first example was write out the complete electron configuration and abbreviated electron configuration for Cl. So what we do is we find where Cl is on the periodic table, and we do that by obviously locating Cl, and we find out that it's at 17. It's right here. That means there are 17 protons in chlorine, which means there are 17 electrons, because there has to be the same number of electrons as there are protons. So what we do is we start at the beginning, at the very top here where hydrogen is, and you'll notice that the 2 I've kind of moved over. That's usually helium, and often you'll see helium over here in row 8 because it has a full electron shell. What I've done is I've kind of cheated a little bit and I've moved it over next to hydrogen because it's 1s1 and then 1s2. So we go across from left to right, just the way we would read something. So left to right, there'd be 1s2, and then 2s2, and then we start the p's at 2p, so it'd be 2p6, 1, 2, 3, 4, 5, 6 for the columns, 3s2 down to here, and then 3p5 would be the final answer. So there's your complete electron configuration for chlorine right here, 1s2, 2s2, 2p6, 3s2, 3p5. If you add all these numbers together, they come up to 17. 2 plus 2 is 4 and 6 is 10. And 2 is 12 and 5 is 17. And that's what we always expect to see. So again, the important points being the S starts at 1s and the P here starts at 2p. Now we can write an abbreviated electron configuration for this as well. And the abbreviated one is usually done by looking at where the element is and then going backwards to the nearest noble gas. And the nearest noble gas here is going to be number 10, which is neon. So we start here at neon, and then it goes 3s2 and then 3p5. So the abbreviated form of the configuration would be neon in square brackets 3s2, 3p5. But the important point being that we always go backwards to the nearest noble gas. The nearest noble gas here being number 10, which is neon. Does anybody have any questions so far?
So how do you determine...
David, I'm sorry, what was that?
How do you determine the abbreviated configuration again? You said nearest noble gas?
Go back to the nearest noble gas, yes. So nearest noble gas, you might say, is argon, which is 18, but the nearest noble gas back from it is neon, number 10.
Okay, but how do you write that? Like, we know it's neon, but how do you enter it and with the abbreviated configuration?
Well, you won't. We won't be dealing with abbreviated configurations on the test. You'll only ever have to do the full ones. But it's always expressed as an element in square brackets, just like this.
All right. Okay.
So let's look at something a little bit more complicated, something a bit more further down on the periodic table. And we'll look at Re. Now, Re is number 75 on the periodic table. You'll find it here. Now, obviously, you're not going to have a periodic table that looks like this. I've got this one here just to kind of shut out any of the noise and just focus on the blocks and how to read the blocks. So the way that it works is we do the same thing as what we did for the chlorine. We start at 1s2, Then we go over to 2s2, and then it'll be 2p6, remembering that the p's will always start at 2p. And then we go down here to 3s2, and then 3p6, and then down here to 4s2. And now the Ds start at 3D, not 4D, right? That can be confusing, but the Ds always start at 3D. So this will be 3D10. And then it'll be 4p6, and then 5s2, and then 4d10, and then 5p6, down to 6s2. Now you'll notice here that what happens is that we're at 56 here, but then it jumps over here to 71 on the 5D. So what happens in between? Well, what happens in between is we have 4F, and 4F is down here. So this, it kind of belongs in this region right here between the 6S and the 5D. So that's the 4F, and the F starts at 4F here. So that'd be 4F 14, and 14 because there's 14 columns in the F block. And then we go up here to the 5D, and this will be 5D5. So the total electron configuration is as it's written right here. Noticing, of course, that when we get down to the 6S, it jumps down to 4F14 and then up to 5D. Does anybody have any questions?
So
you go on.
So like for the block D,
Mm-hmm.
there has to be 10 electrons in that shell for it to be stable, not 8.
Well, it's not so much about stability. There's going to be 10 electrons in the D block. Five total orbitals, but 10 electrons.
Okay,
But it's not really about stability here so much.
All right, so it's just that because my understanding is just like, I know that like these are orbitals, and if the orbitals are full, then that means that it's stable. But like,
Well, certainly that's true if the P block's full, because then we're talking about noble gases. Not so much in the D block, but there is a little bit of stability there in the D block. But the 1s is going to be one orbital that contains 2 electrons. The 2p would be 3 orbitals containing 6. But yeah, I get your point, Roland. The 3D, 1, 2, 3, 4, 5. And again, 2 electrons in each. And then the 4F is 7, with 2 electrons in each, which is where we come up with the 14. All right, so that's what they all look like. So each of these individual lines here, I'm calling an orbital.
Okay. So it's not an orbital that contains 10 electrons. It's two. It's like 3 individual, 4, 5 individual, 7 individual orbitals containing 2 electrons each, and that's what makes them balanced.
That's right. Yeah. Now the 1s, that's the one that looks like a sphere, and then the 2p. Okay, just going back to the previous page here. Yeah, here we go. Sorry, the p's here. That's each individual p orbital right there. Those represent where you could expect those electrons to be. This is the kind of space you'd expect to see them in.
Mm-hmm.
All right. Any other questions?
Thank you for that.
Okay, no worries. Okay. So that's what you'd be expected to do on the test. I'll give you an element and you can write out the full electron configuration. The abbreviated electron configuration for this one, going down here, again, we go back to the nearest noble gas, which would be 54, which happens to be Xe, I believe. Yes, Xe. So Xe would be up to 54, and then 6s2, then down here to 4f14, and then 5d5. So that's what the electron configuration would look like in the abbreviated form for Re. All right, any questions? So what you can also do is we can go ahead and write out actual electron configurations, putting in all of the elements here. And what we do is we can write out what these look like, the 1s, the 2s, the 2p, the 3s, the 3p, and the 4s, as actual lines with orbitals. So the s's are always 1 orbital and the p's are always 3. So you can see that when we're setting it up, we can just set it up the way we were reading it earlier. Now you can either set them up in a straight line like that, or I usually actually set them up as levels like this, but it's really the same thing. And this forms a template for any element up to calcium, which has 20, 3s, 3p. And then you'd have 4s up here. Now the question here is, what would you do to draw the levels for nitrogen? Well, we'd have energy down here or on the side here. Now nitrogen has 7 electrons in it, and I know that because that's where it is on the periodic table. So what I do is I fill in the electrons, always starting at the bottom. That's called the Aufbau principle. Start at the bottom, work your way up to the top. So I put 2 on the bottom. I'll put 2 in the 2s as well. Now, when we get to 2p, you can see we've got 3 energy levels that are equal. So we apply what's called Hund's rule, H-U-N-D-S, Hund's rule. And what we do is we put 1 electron in each. And if we had more electrons, we would just fill in the 2p before we moved on to the 3s. But we have to put 1 electron in each. So that would be the electron diagram for nitrogen. That's how it would look in the way I've got it, with the energy levels shown going up, but this is how it looks when we just do it out to the side like this. I think in a test I've got it written out like this one, which is really the same thing. Does anybody have any questions?
So for the diagram that you're drawing, I thought that P had like more slots than 3. I don't know what the correct word would be, but
well,
P can go up to 6, and you only put 3 for 2p and 3p.
Yeah, well, actually, I didn't put any in 3p because we didn't have the electrons to do that.
Right.
Let's go. Yeah, so let's look at the periodic table. See where nitrogen is? It's here, right?
Yeah.
Right. So we do 1s2, 2s2, but we can only put 3 p orbitals in because that's as far as we got in the p block.
Okay, I see. All right.
Now, if we got to oxygen, I'd put another one in, then fluorine, and then neon.
Well, what for 1s and 2s? Why didn't you put 2 different lines, each with 1 energy level in it?
Because each s orbital is only contains 2 electrons. So the 1s1 would be hydrogen, 1s2 is helium. Then 2s1 would be lithium, 2s2 would be beryllium.
But doesn't nitrogen have 1s2 and 2s2?
It does, but then it finishes at 2p.
Okay, I'm just a little bit confused with how you drew the diagram. That's all. I guess. I mean, I fundamentally understand the concept. So.
Well, I mean, if you wrote it out, it would look like this. It'd be 1s2, 2s2, 2p3. 2 plus 2 plus 3 is 7. So, this represents the 1s block, which is right here. And then you've got the 2s block, which is right here with the lithium and the beryllium. And then we start the p block over here at B and go to C, go to N. That's it. And that's as far as we go. So it's 1 electron per element.
Okay. All right. Thanks for explaining that.
Okay. Anybody got any other questions? So I only would ever ask this for anything between 1 and 20, because it becomes a bit more difficult. It becomes much more difficult to do anything after we get 20, because the energy levels become a little bit less clear. The 3D, for example, is sometimes even represented as being lower than the 4s in certain circumstances. So, you know, we don't want to go too far and have to deal with those kinds of exceptions. All right. So let's look at something like how many unpaired electrons does oxygen have? Well, in order to do that, what you need to do is do exactly what we just did, and that is draw out the energy level diagram. I'm going to cheat a little bit here and just cross out some of the stuff I already did. Okay, so for oxygen, we're looking for the number of unpaired electrons that it has. If there are going to be unpaired electrons, you need to understand that the only place they could be is in the outermost or highest energy orbital that we're drawing. When we do the electron configuration for oxygen, which is 8, it's going to be 1s2, 2s2, 2p4. So there's our 1s2, 2s2, and now we need 4 electrons in the p orbital. So we do 1, 2, 3. Remember, we have to do one at a time first, and then put the fourth one in the first one here like this. And if we're looking for the unpaired electrons, the only place they could ever possibly be would be this orbital right here, the topmost orbital, because all the other orbitals will be filled. They'll always be paired. So this one would have 2 unpaired electrons. So what's the relevance of the unpaired electrons? Well, generally, and I'm just being very general here, the number of unpaired electrons will generally define how many times this will be inclined to bond to other things, because the unpaired electrons are electrons that want to be paired with something else. Does anybody have any questions about the unpaired electrons? Okay, 2 seconds, please. Hello. Hello. Sorry about that. I was expecting some work people to come, but actually it wasn't even them. All right. So let's see. The other thing that we'll look at here is oxidation states. And this is a bit annoying to people, generally speaking. They don't like it. But I don't even think I put it on the test. But oxidation state, I will go through it just because, you know, you will see it in the homework. What we know is that with oxidation states, it's really just a charge on something. And there are certain charges we know and certain charges that can change on certain elements. So if you've got a compound like CaSO3, we know what the charge on Ca always is. We know it's +2 because it's in group 2. And we know that oxygen is always -2. So we know that's +2, and we know each of those oxygens is going to be -2. But what we're interested in here is what the charge on sulfur would be if we knew that those other charges were +2 and -2. So the rules are that we have these oxidation numbers, and then all oxidation numbers add up to the charge on the compound. Now, CaSO3 is neutral, and we know that because there's no charge on it. So if I wanted to find sulfur, we could do a little bit of algebra here, and we could say it's going to be Ca plus S plus 3 times O, and all of that has to add up to be 0. And that would mean 2 plus S plus -6, 3 times -2. And that all adds up to 0, which means that S would be 4. So we can just do some, so that would be the effective charge on sulfur in that compound. And it can vary depending upon what else we have here. So CaSO4 would be different. It would have S being 6. So that's the relevance of it there. We use it a lot when we're talking about balancing for electrons, and that's not something we're going to do too much here. But just something a little bit more difficult. Look at CrO4 2-. And here we're looking for the oxidation state of chromium here in CrO4 2-. So based on what I just said, it would be Cr plus 4 times oxygen is going to equal -2, which is the total charge on the compound here. So it'd be Cr plus, that's not a 0 by the way, it's oxygen, times -2 equals -2, which means chromium would be 6. So +6 effectively would be the charge on the chromium. So that's the basics of it, the very basics of how to determine the oxidation state on something. It won't be a test question, but you will see it in the homework. Does anybody have any questions about the oxidation states? Okay. David, were you going to ask something? No. Okay. So let's look at Lewis structures. Now, Lewis structures, what we're doing here is we're trying to define the bonding and how to draw out what compounds look like, given that we know that there'll be 2 electrons in a bond, and how many valence electrons are going to be involved in the bonding based upon the elements we have in the compound. So let's take a look at an example here. This one's fairly simple. So we've got something like CH4. So CH4, the number of valence electrons we're dealing with is going to be 4 plus 4 times 1, which is 8. Now, how do we get the number of valence electrons? Well, what we do is we use the groupings on the periodic table. So let me go back to the very beginning, the first page here. So you can see here we've got these, well, I haven't got them drawn in here, but that's 1, that's 2 on the hydrogen helium groups. And then we've got 3 over here, 4, 5, 6, 7, 8. So that's those are the numbers that I'm talking about on top of each of the columns. And this is how we can define the number of valence electrons. Now, what are valence electrons? Valence electrons are the electrons in the outer shell. They're the only ones that are capable of being involved in bonding. So that's why I've got them listed here. So 1, 2, 3, 4, 5, 6, 7, 8. So you'll have to be aware of those numbers whenever you're trying to determine how many valence electrons you have or how many valence electrons you're dealing with. Take it right back one more page. There we go. Anybody have any questions about the valence electrons, how we get them? So carbon was in group 4, that's why I've put 4 here. And then hydrogen's in group 1, and there's 4 of them. So that's why I've put 4 times 1 there, so a total of 8. So it makes sense if we're dealing with bonding, we could only deal with valence electrons, which are the only electrons that are involved in bonding. So the first thing we do is we go ahead and put 4 hydrogens around a carbon like this, and then we can bond. And each of these lines represents 2 electrons. So sometimes I'll represent electrons as crosses like this, but each bond represents 2 electrons. And these electrons are shared. It's a covalent bond. So the electrons belong to both the carbon and the hydrogen. They're shared. So carbon, if you count up the number of electrons that we've used, we've got 2, 4, 6, 8. So we've used up all our valence electrons. And that's one of the rules that we have to abide by when dealing with Lewis structures. We must use the exact number of valence electrons that we calculate. So I'll abbreviate that VE. All right, excuse me. Hello? Yes. Uh-huh. Okay. All right, you can park in F4. Well, it should be big enough for you, but, oh, okay. Well, I mean, that's, I think the one next to it is probably okay to park in as well, so I think it's okay. F4, yeah. All right, no worries, fine. All right, sorry about that. That's what I was waiting for. Okay. So we must use the number of valence electrons that we calculated here. Let's look at something a little bit more complicated. Let's say we've got SO3. Now, SO3, if we count up the valence electrons, both S and O are in group 6. So that's why it's going to be 6 plus 3 times 6, which is 24. Is everybody okay with the 24 there? And the fact that S and O are in group 6? Okay. So what we do is we know that we have to use 24. We cannot use more, we cannot use less than that. So we bond, well, we draw the S's and we put the S's and the O's, and we put 3 O's around the S, and then we bond them. At this point, I've used 6 electrons. 2, whoops, not put a dot there. 2, 4, 6, right? That's what we've used so far. The next thing we do is we want to make the outer atoms happy. And by happy, I mean we want to have them have an octet. Because the whole point of this is that everything wants to have an octet at the end, except for hydrogen, which is effectively just needs 2 to be like helium. So what I do is I'll put another 6 around the oxygens here. And I always put them in pairs. And the reason I'm putting in 6 is so that they each have a total of 8. But I do that, and you'll see that once I've put all those electrons in and I've made everything happy, in the oxygens at least, you'll see I have used 24. So I can't use any more. That's it. That's all I can use. But the sulfur here is still unhappy because it's only got 6 around it. So the only way that I can make this happy is to take 2 electrons off one of the oxygens, it doesn't matter which, and share it with the S and form a double bond. So that is usually the hardest part of this is, and that's what people usually have questions about. So, well, when do I know, how do I know that I'm going to need a double bond and when I'm not going to need a double bond? Well, you're always going to need a double bond when you've used up all the electrons and you find out your central element is still unhappy. That's when you need a double bond or a triple bond. So you'll see that once we go ahead and do that, that'll be what the oxygen looks like. Sorry, this oxygen looks like with the 2 electrons and 2 electrons, and 2 of them now are being shared with the sulfur. So now the sulfur has 8, but the oxygens also all have 8 as well. So that would be the correct answer to that. Now, on the test, what I do is I ask you this in terms of a multiple choice. I ask you how many double bonds. So that's going to be one question, and it's multiple choice. And in this case, the answer is going to be 1. Sometimes it can be 0, sometimes it could be 2. The other thing I ask is how many lone pairs. Now, lone pairs are also called non-bonding electron pairs, which kind of makes a lot of sense because they're not involved in bonding. So let's count the number of non-bonding electron pairs we'd have here. We'd have 1, we'd have 2, 3, 4, 5, 6, 7, and 8. So that would be 8 would be the answer to that. So you won't actually, well, I mean, I think you'd have to draw it out in order to get the correct answer, but that's what you're aiming to do, is either to count the number of double bonds or to be able to count the number of lone pairs or non-bonding electron pairs.
Isn't it 10?
Is it 10?
I guess that 2 in the center, because 8 and that doesn't equal 24.
But you know, there's a lot involved. There's bonding electron pairs as well. So there's nothing on the sulfur because they're all involved in bonding.
Oh, so the question's only asking for specific lone pairs, not the ones in between the sulfur and the oxygen then.
Right, but yes, lone pairs, which are, and you've got to be real clear about this, Ron, non-bonding electron pairs.
Okay, gotcha.
So electron pairs that are specifically not involved in bonding.
Gotcha.
Is that okay?
Yeah, that makes sense.
As long as you're clear about that, you'll be good. All right, let's take a squiz here at the next example, and this one involves a polyatomic ion. Now, when we're doing the valence electrons for polyatomic ions, we need to be able to account for the charge on the polyatomic ion. So for example, if you had NO3 minus, you account for that minus by adding a valence electron. We do this because electrons are negatively charged. For PO4, 3 minus, we'd add 3 valence electrons. And then if it was something like NH4 with a 1 plus on it, we would subtract 1 electron. Again, a positive charge, meaning that there's the absence of a negative charge, which would mean the absence of an electron. So if you had something like SO3 2 minus, it would be, valence electrons would be 6 plus 3 times 6 plus 2. Which would be a total of 26. So each of those sulfur and oxygens are in group 6. So that's where I'm getting the 6s from. There's 3 oxygens, so that's why it's 3 times 6. The plus 2 is for the 2 electrons that are resulting from the -2 charge on the SO3 2 minus. So I do the same thing. Does anybody have any questions about that? How getting to 26? Okay, so I'll bond the oxygens to the sulfur, and then I'll put electrons around the oxygens to make them happy, just like we did previously. Now remember, we've got 26 to use here and not 24. So that's 24 used up now, 6 on each oxygen, and then 2 more on the sulfur. That's for a total of 26. Okay, so that would be, and then what we do is we put square brackets around it and we put the 2 minus on the outside. And that will give us our complete structure. So the number of double bonds here number of double bonds would be 0, and the number of lone pairs would be, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that one would be 10. Somebody has said 10 earlier for the other one. Does anybody have any questions?
So for the last one, you didn't add valence electrons to S. This time you do. Why?
Because I had 26 to use. So once I had added all of the oxygens, that used up 24. But if you count them up here, 3 8s are 24 and 2 are 26. Now, because I added those 2 extra electrons to the sulfur, that made it happy, which meant I didn't have to add any double bonds to it.
Oh, okay, I get it. I get it.
Did last time.
All right.
And yeah, that's always going to be kind of the question you're going to have to answer. Is everything happy once you've used up all the valence electrons? And that's really the secret to it. Once you've done that, it's fine. All right. Does anybody have any questions? Does anybody have any questions?
Is there going to be an example of one that's going to be like 10 valence or 10 in the shell? So you have to put 10.
No.
Okay.
No, we're going to pretty much stick with examples here, Roland, where we're dealing with strictly 8 electrons. Now, that's not to say that there aren't exceptions. There are, and we will deal with those when we get to test 4.
Gotcha.
But
Okay.
these, we're just trying to keep things relatively simple here, and we'll just stick with the ones that are more predictable, where we're just looking to get full octets.
Gotcha. Okay. Thank you.
But yeah, to your point, yeah, there are examples of compounds where we do have more than 8 on the central atom, and there's also going to be examples where we have less than 8. So we've got excess electrons. We'll have ones that are electron deficient as well. All right. Does anybody have any questions? All right. Well, let's see what we can do. Let's look at the test here then. Oops. 2 seconds, please. Yeah, come on in. Come on in. Hello. Hello. You got cats, dogs? No. You can leave that. You can leave that open. That's fine.
I'm Josh.
Hey, good to meet you, Josh.
All right.
So-
We're trying to figure out the parking situation.
Okay. You can come here. Anything marked visitor.
Yeah, the F4 are the visitors way down there?
Well, there's visitor 1 up next here to the trash cans. There's one there, and F4. That's I can probably usually have. Well, I move my car out of that. Now I could move my car out of the visitor, and then you get parked. There might my car as a visitor, which is down here. Would that be helpful? Well, there's also a visitor slot down here next to but that's, that's a long way away. Yeah, you guys, so, yeah, I understand. Why not just turn around over there? Well, I got it.
All right, we're gonna get this pretty here though.
Okay, no worries. All right. Sorry about that. Let's move on to what the test looks like here. Come on now. This one. Here we go. So I want to show you what the questions look like that relate to what we're talking about here. And we're going to have so questions 18, 19, and 20. So you'll be asked for an electron configuration, and then you'll also be asked to figure out how many double bonds are present, given a Lewis structure, or given a formula here, and then how many lone pairs there are. That's really all there is to it. All right, does anybody have any questions? Okay, so what I'd like to do is I'd like to start. Does anybody have any other Module 12 questions that they want to ask about or talk about?
Will the test be covering example 11 and coordinate covalent bonds?
No, but the homework will. And there's I think I've included something like that in the. So yeah, here we go. I've included something like that in the soft chalk, so you can read about it in the soft chalk.
Okay.
David, but yes, it's only in the homework, but there's nothing on the test about it. But I do have a section in the soft chalk that relates to it. It's pretty easy. Okay, does anybody have any other questions? All right, so let's go ahead and we'll start review then for the test. Unless anybody has any objections. Now the test, remember, is due next Wednesday, I believe. So I was going to do review for the rest of today, and then review on Monday as well, and then the test would be due on Wednesday. But you don't have to do it on Wednesday. You can do it before Wednesday if you want to. Understand though that all the homework will be due on Tuesday night, 11:59 p.m. and any extra credit for getting 80% on sample test, that closes at 11:59 p.m. on Tuesday as well. And I'd strongly recommend getting all the homework done and just doing it all earlier, so that you can take the day off Wednesday. That would be ideal, I think. And remember, test 2 will be done on a lock, just like test 1 was done. All right, does anybody have any questions just about the procedures, what you're going to do over the next few days?
You said the homework was due on Tuesday along with the extra credit for the test, and the test is due on Wednesday night.
That's right, but you don't have to do the test on Wednesday. You can do the test earlier.
Okay, yeah, I know.
I don't know if anybody's done the test yet. I haven't looked, but people could have done it by now. It's possible. I can't deny it.
And how many questions are on the test?
It's the same as what you're seeing here. It's not that many. I think it's, 19, 20, David.
Okay.
And as far as what's on the test, I can give you actually give you information about that as well. Let's go back to the thing. I have this study guide that tells you the exact kind of questions that are possible for each question type. So if you look at here, study guide, it's very transparent. It tells you exactly what kinds of questions you should be expecting.
Okay.
All right. So I would definitely look at that. You'll see here that for some of them, let's say, let's look at, say, number 14. It says solution stoichiometry, and these are the possibilities. You could start off with a molarity and volume and be looking for a molarity, or you could be starting with molarity and volume, be looking for a volume. Start off with grams, be looking for a molarity, and start off with grams and be looking for volume. So those are the four possibilities, but you only get one of them. But it's very transparent about what you could possibly get. Now, of course, in order to see all those different possibilities, you probably have to do the sample test multiple times, and that's the whole point.
Yeah, I made that mistake last time. Like I got 100% on the sample test, then took the test. A lot of questions I was unfamiliar with and scored like an 80. So
right, well, yeah. So that's why I'm always preaching about doing the sample test multiple times. I would recommend, if it was me doing it, I'd recommend doing it, say, 3 times, open book, right, with all your study materials out, and then I'd close everything and just do it closed book until I was getting at least 90%.
Yeah, that honestly makes sense, considering I didn't know this until after I took the test, but I looked at the grade book, and the tests are worth like 90% of your grade. Like, it's crazy. Like, first test is like 350 points, and then each quiz is like 5 points.
Right. So yeah, the homework is actually not worth that much.
No, it's not.
But it's still worth doing. It can determine an A grade or a B grade, definitely. If you don't do the homework, then you're starting out at a B.
Yeah.
And you, or a C even, possibly. So that's why it's going to be necessary to at least do some of the homework. You have to do all of it, especially if you do some of the extra credit. If you do the extra credit on tests, that gives you 5 points that you don't have to do for homework. That's the way I'd be thinking about it. But still, I guarantee you, only half the people will do the extra credit.
Yeah.
Only half the people. And it's, I don't know, I think people are allergic to extra points. Some people, it's just against their religion or something. I don't know. They don't want the extra points. They say, oh, look, Dr. Musgrave, I don't need them. I don't need them. I'm good.
It's just they procrastinate until the day the test is due.
Oh, no, David, that would never happen. David, no. That's no. No. There's no way that would happen.
Of course, yeah.
All right. Anybody have any questions? Just in general about this? Okay.
So the test is due.
Okay. Sorry.
So the test is due Wednesday night then, right? And that's expecting us to take the test on Wednesday, but we can take it beforehand, right?
Yes, absolutely. Yeah. And I would recommend doing so, just in case you run into any problems. Let me close the door here, please. 2 seconds. I'm working in here, so I'm just going to close the door, but you guys do what you need to do.
Okay, we're not doing in there?
No.
No? Okay.
No.
I like to discuss it with the customer when I get into the place.
So the only thing that you're doing
Okay.
is this room
Mm-hmm.
and that little hallway there.
Okay. And going up into here?
Yes.
Okay. All right. What about the front? Is the tile stays in the front, right?
The tile is staying.
Okay.
Yes. So this little hallway here.
Okay.
This big area here. This tile staying.
Okay.
And that tile staying in the front.
Okay.
All right. So I talked to Anne-Marie, and what she had said is, well, I don't want to, if it's going to look like more than 20, 25 bags, I don't want to be doing it. Okay. Right. So I want you to be sure before you start laying the concrete that you're going to need less than 25 bags.
Okay. Well, I have to get the carpet out and see what I have.
I know exactly right. But what I'm saying is it's more than 25. I'm going to be telling you that I don't want it. I don't want the vinyl flooring. I'm going to go half of the set.
Okay.
Right? Because it's going to be way too expensive to get the thing done.
Mm-hmm. Okay. We're here to work with you. Yeah. Yeah. All right.
Okay, we all clear on everything here?
Yeah.
Okay.
Yep.
All right, thank you.
Mm-hmm. Your.
All right. So let's start with the sample test here, and it's just everything on is that we covered. You know, from module 7 through 12 is what we're looking at. You'll notice that on the test, and this is going to be the same with the test you're taking, the periodic table is present at the very beginning, along with a list of elements, right? So there shouldn't be any problem with saying, oh, I don't know what that element is. You'll always have access to all of this on the real test as well. So you won't need these materials in front of you as printed sheets. In fact, I don't want you to have that. You know, this is completely closed book, what you're doing when you're taking the real test. Now, when you're doing the sample module test, obviously you can do that open book as often as you like, but I still recommend that after you've done it open book a few times, that you do it closed book a few times. All right, so let's take a look. I guess I'll just go through this test. Understanding though that these questions can vary depending upon the question types, and those question types are outlined in the reference, in that study guide that I showed you just a couple of minutes ago. Is everybody clear on this? Does anybody have any questions, any doubts, any concerns about the test so far? Nothing?
The only part that I'm not sure on is some of the questions from module 9.
Okay, well, we are going to go through those anyway, Emily.
Okay.
Yeah, I mean, I'm just going to go through an example of a test, right? I'm just going to start from the beginning and just run my way through. Is that okay?
Yeah, thank you.
All right, so we're starting here at modules. This is module 7. And the first 4 questions are from module 7. And you can reference back to the study guide to know exactly where these are, which module these are from. All right, so let's see. We've got one atom of Ga here, and we're looking for the mass. What's the mass of one atom of Ga? So what I would do is I would write that out first. One atom Ga. And you can see that of course it's written here for us. And we know that in order to make this work, this is going to have to be atoms of Ga on the bottom, or atom Ga, or atoms, it doesn't really matter. And then on top, we need grams of Ga. So we need some kind of relationship between grams and atoms of gallium. Now you can look here and you can see that we have the relationships all lined out for us. We don't have to memorize any of these numbers here. And you can see that the relationship that we can use here is the molecular weight in grams is equal to 6.022 times 10 to the 23 atoms. So that's exactly what I would do. You are given the molecular weight in the problem, 69.72. So you don't even have to look that up. And it's 6.022 times 10 to the 23, or E23 atoms of Ga. And these are the numbers, of course, that will go into 1 and 2 of your answers. And then when you're figuring out the number of significant figures, it's going to be 4 significant figures. For this one, it's really important that you, let me see, have we got the, yes, I do have the on-a-lot calculator here as well. This gives me an opportunity to show you how you would enter this into the on-a-lot calculator. And now on the test, the on-a-lot calculator doesn't come up like this. It comes up as a button that you press where it says scientific calculator. Oh, let me open that in another tab. I'm sorry about that. I didn't mean to. See, it's going to let me go back here. Let me open a new tab. I recommend you do this as well. Open in a new tab. So for this one, it's going to be 1 times 69.72. So I put 69.72. And then divided by, and it's going to be 6.022 times 10 to the 23 atoms of Ga. So you write in 6.022, and then you've got the EE button here. That's your exponent button. Hit that. You'll notice it gets gray, dark gray, which means it's active. And then you hit 23. And then you hit equals. And that'll give you the correct answer. Now this is going to be 4 significant figures. So what I would do is I would write 1.158 E negative 22 grams of Ga would be the final answer there. Does anybody have any questions about anything I just did there? Any questions? Okay. Now the next question here, let's see, is question 2. Okay, we've got 110 liters of Xe, and we're looking for the grams of Xe. So again, I would do the same thing. I'll do 110 liters of Xe, then times. Now I want grams of Xe, so notice my technique here, how you can have a scrap sheet of paper on the test. Notice how I'm writing out the units first, and then I put the numbers in at the end. And now we're looking for a relationship between grams and liters. And the grams and liters here would be grams of Xe, liters of Xe, and the relationship is molecular weight to 22.414 liters. So I'd write in 22.414 liters on the bottom, and then on the grams it would be the molecular weight, which is given in the problem, 131.29. See, it really couldn't be much easier than that. And then you would go ahead and you enter that into the calculator. And I'd go 110 times 131.29 divided by 22.414. Hit equals, and there's my answer, 644. Now, looking at what we're beginning with here, though, we've only got 2 significant figures. So our answer comes out to 2 significant figures as well, which means it's going to actually be 640 grams of Xe. Now, understand that if you did write 644 as your answer, you'd still get 9 out of 10 for the problem, but you wouldn't get 10 out of 10 because the significant figures weren't correct. Does anybody have any questions? Everybody's fine up to this point, hey? Okay. We've already done a similar one to this, 1 atom of Al. Understanding, of course, sometimes you're going to see any attempt you take, you can see the same problem type a couple of times. Not exactly the same problem, but the same problem type. Like this one, we've already done an example of a mass of 1 atom of something. We did that previously. But, you know, it's possible you could see it again, but on different attempts, you might get 3 different ones. So you've got to be prepared for all of them. So let's look at number 4 here. Now, number 4 is always going to be of this type. It's going to be one where you will have 2 steps that you'll need to do. Okay, so we've got 3, 4, 7 grams of PCl5. And then we'll have our we'll have our 2 steps, and we know there's 2 steps because, well, you've got them written out here. So that's why I'd recommend going ahead and just going and doing this, you know, just writing it out on a scrap sheet of paper to make sure you've got everything under control. So remember my technique. I always like to put in the units first. So grams and PCl5, units and compounds, of course. And then over here, what do I want at the end? I want atoms of Cl. Now, the reason we're doing this in 2 steps is because, well, we can't do it in one. That's the reason. There's no relationship that allows us to get from between grams of PCl5 and atoms of Cl. So we have to do it in 2 separate steps. So we need a linking unit here, something in common, and that would actually be the molecules, and be molecules of PCl5. So I'll go ahead and do that. So I know that those are going to be the relationships in each case. So, you know, again, look at my technique. Look how I'm just putting in the units and then I put the numbers in. So the relationship between the molecules and grams, 6.022 E23, and the number of grams of PCl5, which is 208.22. So that's the molecular weight right there. Then we've got 5 atoms of Cl to 1 molecule of PCl5 is the relationship between atoms and molecules. That's why we had to use molecules here as our linking. So we go ahead and we can put all that into the analog calculator. Where are we? Clear. And we would have 347 times 6.022 23 divided by 208.22 times 5. So that would be our answer there, 5.017851 times 10 to the 24th. But again, we want to look at the number of sig we have at the beginning, which is 3, which is why the answer would be 5.02 E24, and the unit would be atoms of Cl. All right, does anybody have any questions? Anybody got any questions about that one? Okay, well, that seems like a good place to stop. So we're at the end of module 7, and we'll start afresh on module 8 on Monday with the review. If anybody wants to set up a time with me to talk about anything, you're certainly welcome to do so over the next few days. But again, follow my advice. See if you can get that test done early. Don't wait till next Wednesday to do it. All right. Does anybody have any questions? Last minute questions? Okay. Well, I'll see you all later. Thanks for coming today. Sorry about the interruptions.
Thank you, Professor.
Hopefully it won't be like this next Monday.
Have a good day.
Thank you. You too. I'll see you all later. Okay, so who's left here? Christina, Marta, Richard, Thomas, Coloni. Does anybody have any questions? Anybody here at the end here? Anybody have any questions? Okay, I'm going to end the meeting then. Thank you.